Hello everyone and welcome to a video on resultant forces. What I'd like you to do first of all is to watch a different video on YouTube. I'll give you that link in a moment, and after that we'll just go through some free body diagrams, some resultant forces, and then we'll look at some questions. You will need today a pen and paper, maybe a calculator, depends how good your mental maths is, and obviously a pen or a pencil. So we'll start with the video. So if you type in bit.ly/resultant forces, that will bring up the video on YouTube that I'd like you to watch. You will need to type that in. I don't think by clicking on the video the link will work, so do type it in, or maybe your teacher has given the link to you on Show My Homework. Now that you've watched the video, hopefully you've got a good understanding. I'm just going to go through it again in just a different way, and then together hopefully you'll understand a little bit more about free body diagrams and resultant forces. So a free body diagram models the forces acting on an object. The object or body is usually shown as a box or a dot. The forces are shown as thin arrows pointing away from the centre of the box or dot. So we might have a dot, and on there we might have two forces acting, and that might be the weight acting down, and if it's something falling through the sky, we might call the drag air resistance. Generally speaking, there will be two forces acting in opposite directions. Occasionally, more complicated free body diagrams might include arrows going left and right. Now, these diagrams don't need to be drawn to scale, but it can certainly be useful if they are. A reminder, a force is a vector quantity. The arrows represent the direction, and the size of the arrows can also represent the size of the force. So certainly you do need a number on these diagrams, and we'll go through some examples in a moment, but if you can draw it to scale, that makes it even better. If we have a box on a table, there are two forces acting on it, one going down and one going up. Now, the force is happening between the box and the table, so that will be just there. So the weight is going down, and we always call the upward force, in this case, a reaction force. So let's just put some numbers on there, because we said a second ago that they're important. Well, let's say the weight of the box is 50 newtons. Now, because the box is not accelerating, it's not speeding up, it's not slowing down, it's staying at a constant speed of 0, it's not moving, then the forces are balanced. So if 50 newtons are acting down, that means 50 newtons must be also acting up. And that means the resultant force is 0 newtons, because we've got 50 newtons acting down, and then we take away, because it's in opposite directions, 50 newtons acting up, so that gives us our 0 newtons. If we have a box that's falling through the air, again, it's going to have a downward force of weight. Now the upward force here might be, say, air resistance or drag, and if the weight is still 50 newtons, but this time the air resistance is only 20 newtons, like before, we can take one force away from the other to find the resultant force. So the resultant force equals 50, the one that is going down, take away 20 newtons, the one that's going up. So our resultant force is 30 newtons, and because it's a vector, we need to give a direction, so downwards. So this means, because there is a resultant force, as in it's not 0 newtons, the forces are unbalanced. And if they're unbalanced, that means the object is changing speed or changing velocity, and the object is therefore accelerating. So it's accelerating downwards. So I've gone through how to draw free body diagrams, and you should have seen the video at the start as well. And I've also just briefly gone through how to do resultant forces. So what we'll do now is we'll have a go at some examples, and this is when you'll need to press start and stop to give you some thinking time, some writing time on that notepad that you should have in front of you. So if we wanted to find the resultant force of A and B, have a look at the diagrams, and in your book or on a piece of paper, write down the resultant forces of A and B, remembering to show any workings that you have done. So press pause, and then when you press play again, I will go through the answers. Okay, the answers. For A, there's only one force, so the resultant force will be 5 newtons to the right. Remember, direction is important. For B, we've got 2 forces and they're in opposite directions. So 6 take away 4, and that gives us 2 newtons, and it's the 6 Newton one that's the largest, so it's to the right. Again, have a look at the questions, C and D, try and find the resultant forces. So press pause, and when you're ready, resume. Okay, so we've got 2 opposing forces in opposite directions, so we take them away from each other. So the resultant force here is 0 newtons. So if we add to what we know, that means that we've got balanced forces, so the object is remaining at a steady speed or stationary, is not moving. For D, again, we take the forces away from each other because they're in opposite directions. So 7 take away 5, so that gives us 2 newtons, and that's to the left. And because we have a value here for resultant force that's bigger than 0, it's an unbalanced force, so that means the object would be accelerating. For the next one, slightly trickier in that we've got more forces acting, so you need to treat all forces acting in the same direction together, so you add them and then you take them away from the forces acting in the opposite direction. So again, press pause, and when you're ready, restart. Okay, so we treat these two as 1, so 7 plus 4 gives us 11 newtons. So we've got 11 newtons to the left, we've got 5 newtons to the right, so 11 take away 5, so that gives us 6 newtons to the left. For F, again, we treat those two together because they're in the same direction, so that's 9 newtons, that's 5 plus 4, and then we need to take it away from the 9 newtons acting in the opposite direction, so then we have 0 newtons. So E is unbalanced, and because it's 0, we'd call that one balanced. Again, slightly trickier in that we've got 4 forces to take into consideration, so again, press pause, have a go, and then when you're ready, we'll go through the answers. So on the left-hand side, acting in the same direction, 10, 6 plus 4. And on the right-hand side, 13 newtons, 7 plus 6. So then we can say 13 minus 10. The difference between the two is 3 newtons, and it will be towards the right. For H, 6 plus 5 is 11 newtons. 7 plus 4 is 11 newtons. And then because they're in opposite directions, we can take them away from each other. And again, we get an example of a balanced force, which equals 0 newtons. Again, a couple more, have a go, and when you're ready, press start again. So we've got 11 newtons acting to the right, we've got 10 newtons acting, 11 newtons to the left, 10 newtons to the right, 11 minus 10, so that gives us 1 newton to the left. And on the left we've got 9 newtons, on the right we've got 11 newtons, So 11 minus 9 gives us 2 newtons, and that would be towards the right. A couple more examples to look at. So again, when you're ready, press pause and resume once you've given them a go. So 6 plus 4, 10 newtons. 7 plus 5 gives us 12 newtons. Opposite direction, so we can take them away from each other. So that leaves 2 newtons to the right. Slightly different this one in that it's been rotated, so we've got up forces and down forces rather than ones on the left and on the right. Still, you treat them the same. So any force acting in the same direction you add, so that's 14 newtons going up and 6 newtons going down. So they're in opposite directions. 14 take away 6 gives us 8 newtons, and then that would be going upwards. Final example just here, M and N. Now before you have a go at N, you need to just be aware to treat the forces that are opposite each other together. So up and down and left and right separately. So press pause, give it a go, and when you're ready, resume. Okay, so we've just got 7 and 6 newtons. They're in opposite directions, so this one's perhaps quite straightforward. 7 minus 6 gives us 1 newton acting down. Now, N might look quite complicated because there's 4 different arrows and they're all in different directions. But let's do the horizontal ones first. Let's break it down. So we've got 6 newtons to the left and 6 newtons to the right. So in the horizontal plane, there's 0 newtons. And if we look at the ones going up and down, we've got 7 newtons and 7 newtons. So they go in opposite directions again. One minus the other gives us 0 newtons. So overall, this would be a balanced diagram because all the forces cancel out. So the object is in equilibrium. It's either not moving or moving at a constant speed. There's no acceleration. The resultant force is 0 newtons. So we'll just look at some final few questions. And again, press pause, have a think, and then we'll go through the answers one by one. So the first one, what rules must be followed when drawing force body diagrams? So write down probably, well, I can think of about 6 different stages. Think about what you have to do to draw a force body diagram. Okay, so firstly, you want to be able to identify the body or the object that you want to make a force body diagram of. And then what you want to do is draw a simple representation of the body. You also need to be thinking of the forces that are acting on the body. The fourth step would be to draw the forces one by one, making sure that you use arrows pointing in the direction of the force. You'll then need to label your forces properly. And what I mean by that is make sure you name the force. So if you're labelling weight, call it weight rather than just a force. And then the final step will be just to check everything over to make sure that if you have to draw it to scale, that you've drawn it to scale, that you've labelled everything and you put any numbers on that you need to put on there. Okay, the second question. So again, press pause when you're ready, but what happens if an object has a resultant force of 0? So if the resultant force that you've calculated is 0 newtons, what happens? Press pause. Once you've had a go, press play again. So if we just look at an example, we might have 2 forces, 5 newtons and 5 newtons. So those forces would cancel each other out to give us a resultant force of 0. So what that means is we've got a balanced force And if something is balanced, that means it does not accelerate. It doesn't speed up and it doesn't slow down. So the object is either at rest, or you could say stationary, or moving at a constant velocity or constant speed. So this question relies on the video that you watched at the start. What happens when the forward thrust of the aeroplane is greater than the air resistance? Draw the force body diagram to help explain. So here is our force body diagram from the video, and what you can see is the forward thrust is 120,000 newtons and the air resistance backwards is 90,000 newtons. So what happens? Well, if we just look at the horizontal components, they're in opposite directions, so 120,000, take away 90,000, that gives us 30,000 newtons to the right. So what that means is, thankfully the object is moving forwards, it's an aeroplane, so that's good, but it's accelerating forwards with a resultant force of 30,000 newtons. That brings us to the end of this video on resultant forces. So hopefully you watched the video and you've now got a better understanding of how to draw free body diagrams or force body diagrams. You can calculate some resultant forces and you had a go at some of the questions. Well done and see you next time.